Hello everyone. We are going to present the paper of streaming active learning with deep neural networks, which has been accepted in the conference of ICML 2023. This paper deals with the idea of active learning, which is most naturally posed as an online learning problem. The prior works on active learning have mostly assumed an offline access to the entire dataset made available ahead of time. But this paper proposes a novel algorithm vessel, a new algorithm for batch active learning with deep neural networks in streaming settings, which samples the points to query as soon as they are presented. This mainly deals with the trade-off between uncertainty and diversity of queried samples to match a proposed query rate, where we can think of the query rate as the labeling budget divided by the number of points in the entire dataset. Labeling budget can be thought of as the number of points we want to include in a batch of training data. These algorithm finds its application in uh, human-computer interaction (HCI) and large fracture datasets. Now, HCI human-computer interaction, the decision is to be made on the fly to query about any data point, and in case of large fracture datasets, the chunks of the data are distributed in a system and the whole data cannot be made available in its entirety at once. Active learning considers a supervised learning situation where there is an abundance of unlabeled data, but it is expensive to acquire labels. For example, classifying underlying disorders from histological images requires the attention of medical experts. On the other hand, predicting drug efficacy involves intensive experimentation to be carried out in clinical laboratories. In these settings, we typically want to carefully consider what samples to request labels for so that we can make our model with minimum cost. In the convex case, where a model can easily be updated to accommodate for a single sample, active learning algorithms have tended to focus on uncertainty. Now, by uncertainty, what we mean is that we have an unlabeled data point which is very close to the decision boundary. So this point needs to be resolved for its label so that the model can be confident about where the decision boundary should pass through. Also, for high performing batch mode active learning algorithms, we must also consider diversity. Now, if we have two samples which are unlabeled and they are relatively similar to each other, by which we mean that in a space the points are very close to each other, then it is inefficient to query both of them because by label smoothness we can say about the label of one point if we query on the other. So we can have only one such sample labeled and integrate into the current hypothesis, which is enough to resolve the model's uncertainty on the other point. Now we consider the situation. Why a situation of streaming active learning is necessary. Suppose we are having a human computer interaction application where a user interacts with the world while wearing an assistive or diagnostic device. The software on the device might involve a classifier that detects objects being interacted with or the activity being performed by the user. Now, requesting a label to update the model to better classify the phenomena can only be done in the moment. It will be very cumbersome if it queries some uh, labels for an event which has occurred very far in the past. Now, we propose a simple active learning algorithm that is Vessel, volume sampling for streaming active learning that addresses the concerns mentioned above. Vessel is a natural choice for committal situations, where labeling decisions need to be made on the fly. On non-sequential datasets where more conventional active learning algorithms could be exercised, Vessel can be significantly faster, especially for larger batch sizes. Now, despite being simple and flexible, Vessel is surprisingly high performing. Result produces models with predictive capabilities on par with state-of-the-art active learning approaches, even though they are not restricted to the streaming setting. Another advantage of Vessel is that it is hyperparameter free, which makes it a powerful candidate for a wide range of active learning scenarios. Neural active learning algorithms that incorporate diversity can be thought of as making two design decisions. First way, how such unlabeled candidate samples should be represented. Common choices may be we can choose the penultimate layer representation of the current state of the network for a given sample, or we can use a hypothetical gradient that might be induced by the sample. In either case, after the data is sent into that space, now the thing left to do is how should we sample such points so as to introduce batch diversity. In Visual, these decisions are made to produce a high-performing active learner that is amenable to the streaming committal setting. Let's assume that a candidate point represented by xt is seen only once, and that we must make a decision about whether or not to include it in the batch B as soon as possible. And once the labeling budget k is allocated, we retrain the model and repeat the process. Visual performs active learning by the following procedure. Let's say we have a neural network architecture F with parameters being theta, and the last layer parameters be represented by theta L, and let's say the loss function we use for the learning procedure is L, which is the cross entropy loss function. The gradient representation for a sample xt is g of xt equated to the derivative of the loss function with respect to the last layer parameters theta L, where the loss function is computed with respect to the predicted level yt hat and the probability distribution associated with the particular point. So this is nothing but the negative logarithm of the associated probability with respect to the predicted class level yt hat. The main aim behind this equation is to sample such points with high uncertainty. So the points with high uncertainty are those points which are near to the decision boundary. And if they are near to the decision boundary, this gradient will be larger in magnitude. So the way of doing volume sampling is to select a batch of points with probability proportional to the determinant of the gram or covariance matrix. But in general, we use the covariance matrix for this purpose, which the probability mass on a batch of samples B is proportional to determinant of the sigma x belongs to the batch B and the outer product of the gradients, that is gx transpose, where mod B is the length of the batch, which is equal to k, the pre-specified labeling budget. The intuition behind this can be understood like the covariance matrix gives an estimate of the spread of the points, and if we take the determinant of such matrix, what it essentially gives is the volume of the parallelepiped formed by the row vectors of the covariance matrix. And since we said that the covariance matrix gives a measure of the spread of the data points, so if we maximize the volume, then that particular point is said to increase the diversity by the maximum extent. There are several reasons to favor the covariance matrix version over the gram matrix. From a theoretical point of view, when used in an outer product, g of x could be thought of as a rank point approximation of the feature information matrix, which is defined as the expectation over the Hessian of the loss function. As such, this construction is reminiscent of a classic goal in estimation theory perspective, which is to maximize the determinant of the feature. Also, from a more practical point of view, the covariance matrix will stay fixed in dimensionality even as the batch size k is changed. In the gram matrix alternative, it is suggested in as that the size of the matrix grows with k, which potentially becomes intractable for larger batch sizes. A process that samples from a distribution characterized by a determinant like this is referred as the determinantal point process (DPP). Sampling from a DPP is usually done using Markov-Chain Monte Carlo methods. So Weyfeld chooses a sample xt for labeling with probability pt proportional to the determinant of sigma t hat plus gxt transpose, where sigma t hat is defined as sigma of x belongs to b g of x transpose, which is nothing but the covariance over samples that have already been selected for inclusion in the batch. Plus, this term is the outer product of the point currently under consideration. So, using matrix determinant lemma, Pt proportional to determinant of sigma t hat into 1 plus gxt transpose sigma t hat inverse g of xt, And since this term determinant of sigma t hat is already known when deciding whether to sample the point xt or not, so p of t is proportional to g of xt transpose into sigma t hat inverse into g of xt. To compute pt in practice, this proportionality equation, g of xt transpose sigma t hat inverse g of xt must be scaled by some value zt. So we can write this equation pt equal to some zt into this term, that is cxt transpose sigma t hat inverse g of xt. Also, instead of assigning a fixed labeling budget k, we can instead tell to consider q as the query rate, which can be defined as the labeling budget divided by the size of the candidate set. So expectation over pt for all points is equal to expectation over all points of this the currently mentioned equation of pt, that is set t into g of x transpose sigma t hat inverse into g of x, which should be equal to q as mentioned earlier. Now, how to decide over how to choose this value of zt? So expectation over x of zt into g of x transpose into sigma t hat inverse of g of x equal to zt. We can take out this zt term common, and what we are left with is the highlighted term. Also, this highlighted term is a scalar. So the trace of any scalar matrix is equal to the matrix itself. So zt into expectation of x of trace of this term, and trace of sigma t, and this inner term can be rearranged to write it like this. So zt into trace of sigma t hat inverse into expectation over the outer product of the currently uh, considered point. So we can write zt equal to q. This is q as mentioned earlier. So zt equal to q by trace of this. So finally we can write pt equal to the term which it is proportional to, that is g of xt transpose into sigma t hat inverse into g of xt into q by trace of sigma t hat inverse into expectation of this term. Now this expectation over this term, it can be truly derived from the true distribution. But since we do not have it at hand, what we do that we equate it to the estimate of the covariance over the sample terms, that is 1 by t into sigma I equal to 1 to t g of xi transpose is represented in this equation. So to summarize, the algorithm can be written as: we initialize a neural network architecture f which takes input x and parameterized by theta. We have a stream of unlabeled samples u and ideal sampling rate q. Firstly, we initialize the time step t equals 1 and sigma naught hat inverse, which is the covariance of the sampled points, so is equated to 1 by lambda into id, which is lambda is a regularization term for stability. We initialize a naught equal to 0 matrix of dimension d cross d, where a naught is the covariance of all points encountered, whether it is sampled or not sampled. And the currently we have the batch b as a null set 5. For every xt belonging to the stream of unlabeled samples, we first update at as this. Why this? Because at minus 1 is the covariance matrix of the previous t minus 1 samples. Since covariance matrix involves a division by the total number of terms, we multiply it by t minus 1 so that we obtain the summation, and then add it with the outer product of the gradient representation of currently considered point and divide by t to obtain the current covariance matrix. And for pt, what we do is this, which have been derived earlier, and now we sample the point xt with probability as minimum of pt comma 1, and if we sample the point, then we include the particular point and its corresponding label in our current batch, and we update it the sigma t plus 1 hat inverse using this Woodbury update rule. And if we do not sample the current point, we equate the sigma t plus 1 hat inverse as sigma t hat inverse itself, since there is no addition of points. And then we increment the time step, and we may retrain the particular model with the acquired point, and then repeat the process for further time steps.
Okay. The goal of Now that we have explored the theoretical foundation of VSL, let's move on to the experimental evaluation. In this section, we will discuss how VSL was tested against various baselines, the dataset used, the experimental setups, and the key findings. So the goal of these experiments is to evaluate how well VSL perform in streaming active learning settings. The author tested it on multiple datasets and compared it against several baseline methods. So the baseline that are used for comparison are this here it is compared against six baseline. First is a badge that is a non-streaming combines uncertainty and diversity based sampling using k-means plus clustering, followed by random sampling that selects data points randomly, then the confidence based sampling, that is conf, selects sample where the model is least confident, followed by core set selection uses diversity based sampling via k center clustering. Then the vessel pan streaming, the variation of vessel using penultimate layers embedding. Then we have stream uniform sampling, a simple method that sample data at a fixed rate. Coming onto the data set, we have four kind of data set here. First, SVHN, that is a street view house number dataset, followed by MNIST, that is handwritten digit classification, CIFAR10, that is a natural image classification, and clown, a real world dataset of object interaction using augmented reality device. Coming on to the setup, there are two architectures used, a a 2-layer MLP, and an 18-layer ResNet. Then optimizer is an Adam with a learning rate of 0.001 and a batch size of 100, 1K, 10K for the standard dataset and 10, 100, 1K for the cloud. The initial label data size is of 100 samples, that is mentioned over here. Coming on to the IID data stream. Let's first examine the vessel's performance when the data stream is independent and identically distributed, that is IID, means the order of the sample is randomized. Key findings. So vessel matches the performance of the best non-streaming method, that is batch. The outperform of all other streaming baselines. It outperformed all other streaming baselines, proving its efficiency. So coming on to the figure 2, coming on to figure 4, here in this paper present the learning curve comparison of different active learning method across various datasets and architecture. The x-axis represents the fraction of labeled dataset while y-axis represents the accuracy. It is observed that the vessel learning curve closely follows the badges, proving its efficiency. Other streaming methods like stream uniform performance significantly worse. This result highlights that a vessel can match non-streaming baseline despite its streaming constraints. Coming on to the non-IID data stream. Now let's look at a more challenging case when a data stream is non-IID but exhibit feature drifts. This means that the distribution of the data changes over time. Here there are two types of feature drifts mentioned, an artificial drift and a natural drift. An artificial drift introduced by sorting CIFAR10 and SVHN by the first principal component, followed by natural drift observed in the clown dataset where the object label follows the natural order of human interaction. Coming on to the key observation from non-IID dataset that a V-cell still perform as per the non-streaming method like batch even under feature drift. It outperformed all the streaming baseline, demonstrated its robustness. Comparing to the graph of, so after this we can evaluate this graph which is over here. So this presents a comparison matrix showing how often one method outperformed the other under feature drift. So here it is of a non-IID data stream. Each cell represents how frequently a row algorithm beats a column algorithm. So lower value indicates a better performance. So it is shown that the vessel consistently the vessel consistently outperform other streaming method, proving its ability, while the batch performed best overall. Vessel is the strongest among the streaming method. Here the smaller the value, better will be the performance. Coming on to the label amplification, yeah. One of the key goals of active learning is to improve labeling efficiency. That is, selecting the most informative data points so fewer labeled samples are needed to reach higher accuracy. The key findings of the label amplification is Vessel achieves the same label efficiency as Batch in IID settings. In non-IID settings, Vessel is slightly worse but still much better than all other streaming baselines. Coming onto the graph, this. The figure 6 visualize the efficiency of different methods. The x-axis represents the progress of learning, while the y-axis is a ratio of required label compared to uniform sampling. A higher label amplification ratio indicates a more efficient method. Vessel ratio is nearly identical to batch. So here you can see that vessel ratio is nearly identical to batch, proving that it is highly efficient at selecting useful data points. Coming onto its computational efficiency, that is the compute requirement. Now let's examine another important aspect, the computational efficiency. A good learning, a good active learning method should not only be accurate but also computationally efficient. The key finding from this column, the column 4.4, is the vessel compute the time remains nearly constant. Even a batch size increases. Other non-streaming method like batch, corset become significantly slower. That is represented in this graph as well. So if you see the the other non-streaming methods like batch, corset become significantly slower as the batch size increases. This makes vessels scalable and suitable for large data set. So here we come to the graph, to the figure 7. The figure 7 compares the compute time required for different active learning methods as the batch size increases. The vessel curve remains flat, which is shown over here, indicate a constant computational time. The batch and corset show exponential growth, which is this, making them inefficient for a large dataset. This proves that the vessel is highly scalable and computationally efficient. Coming on to the discussion, the key takeaways from this discussion is now let's is that Vessel is the first active learning method designed for real-time streaming data. Despite the streaming constraint, it performs as well as non streaming, it outperforms non-streaming methods. It is computationally efficient and scalable, making it ideal for the real-world application. Coming on to the future research directions, the author also discussed existing possibilities for improving vessel in the future. First is adapting to dynamic label space. Future models show handle cases where the new classes emerges over time. Second, handling query cost. Some label may be harder to or costlier to obtain. Future methods should balance informativeness with cost. Third, expanding to real world use cases. Vessels are ideal for autonomous learning system, robots, and large scale AI applications. So, here we come on the conclusion that to conclude, Vessel represent a major step forward in streaming active learning. It is accurate, efficient, and scalable, making it a powerful tool for a real world AI application. And yeah, that's all. Thank you.